Hi, we're going to be doing this practice problem on type 1 and type 2 error and power and effect size. And we'll start with this problem. A random sample of 800 working men in the Tama area was taken, and it was found that 60 of them have a second job. Go ahead and write a 95% confidence interval for the true proportion. So start with making sure that you do your conditions and show your work and how you got your interval, and then interpret it at the end. So I'm going to pause the video, go ahead and do that, and then I'll pop up the answers. Okay, so here's the answers. We're doing a 1 prop Z interval. Our conditions are IRS 10, so we'll assume independence. It states randomness in the prompt. And notice I said workers here, so that's context. We have NP and NQ both greater than 10, and 800 is less than 10% of all male workers. Running the calculations, our P hat is 60 over 800, which is 0.075. Our standard error is 0.075, is this, 0.075 PQ over N, square root. And then the confidence interval is 0.075 plus or minus 1.96 times standard error. So we're going out and back almost 2 standard deviations from our P hat. This gives us a confidence interval, lower end 0.0567, upper end 0.0933. And our interpretation must be in context. We are 95% confident that the true proportion of male workers, and you might add in Tama with a second job, is between 5.7 and 9.3%. Okay. Well, very good. We're going to go and we're going to do number 2 now, which says a news report says that 6% of the working male population has a second job. So we're going to test this claim using the given sample as evidence that the true proportion may be larger. So we're going to do the same type of test now. We're going to do a 4-prong test. Go ahead and skip the conditions here. Just do the null and alternative, do your calculations, and then your conclusion and context. So go ahead and do the three of the 4 quadrants of your little box there. Pause the video, get it done. Okay, let's walk through this so you can see the answers here. Let's I must define my P. That P is the proportion of men in Tama, I guess in Tama, that have second jobs. P is 0.06 is our null. Our alternative is P is greater than 0.06, and our P hat is 0.075. So now we're going to run this test with an alpha of 0.05. Now I question here, this alpha is matched up to what confidence interval? Because up here up in the previous problem in number 1, we did a 95% confidence interval. Does that match up to this alpha of 0.05? I'm going to let you think about that. And then maybe you could answer me in class if you want. Okay, so Z is equal to 0.075, which is P hat minus P, or P naught, which is our null, okay? And we say 0.075 minus 0.06 is 1.78 divided by the standard error, and then our standard deviation of that statistic, and then we end up with Z is greater than 1.78, or the probability that Z is greater than 1.78, which is this area here, with a standard normal distribution, because we've now calculated the test statistic. This probability is 0.037. In our conclusion and context, since P is less than our alpha, you could say 0.037 is less than 0.05, but you've shown both numbers. We reject H naught and find sufficient evidence to suggest the proportion of men with second jobs in Tama is greater than 6%. On to the next problem. Okay, so the next question says, what alpha level you use? What is the alpha level you use? Well, what is the probability of a type 1 error? Well, they're the same. Alpha equals 0.05. We know that if we use alpha as 0.05 and the null hypothesis is true, then there is a 5% chance, let's say it's a less than test. We did a greater one, but just say for the sake of the teaching here, that we're doing a less than test. If we did a less than test and then alpha was 0.05, when we found our test statistic, then Z is going to fall in this region 5% of the time by random chance alone. So the probability of actually rejecting wrongly, in other words, we reject a true null is 5%. It's going to happen by random chance alone. So usually when it happens by random chance alone, we reject, and we just don't believe that it could have happened by random chance alone, but it actually could, and that's why it's called a type 1 error. Okay? All right. Now, number 4 says if the sample proportion is actually the same as the true proportion, what would the effect size be? And then what does this mean in context? And what is the difference between statistically significant and practically significant? Think about that for a second, and then write your answer down. Pause the video and write your answer. And then after you paused and you've written your answer, come back and I'll give you a solution. Okay, so the effect size here is P minus P naught. So the true P is what our P hat was. That's what we're assuming that that's true. And if that is true, then 0.075 minus our hypothesized P, which is 0.06, is our effect size. And we aren't sure of practical significance, but we do have statistical significance. In other words, the probability of us getting a result more extreme than ours by random chance alone, we found on the previous slide to be 33.7%. So only something more extreme than us can happen only 3% of the time. However, this could have been done by random chance alone, but it is statistically significant. Now, as far as practical significance, is it practically significant? Does it really mean a whole lot that 7.5% of the men in Tama have second jobs versus 6%? That may be up to consideration by the Tama government or by the Japanese government. They might not believe that it's really a big enough difference for us to be worried about it. Perhaps if they saw 10% of the people had second jobs, they might be concerned that, wages are too low, or there's a recession, or some other problem is going on. So practical significance is not the same as statistical significance. Okay, on to the next page. Okay, so now this problem asks you to calculate the probability of a type 2 error using the sample proportion as the true proportion. Okay, so we are using H naught, and our H naught is 0.06, P equals 0.06. And then we have a normal distribution that we're going to be doing our analysis of our problem on this curve that has this P and this standard deviation. So we are basically trying to figure out what is this P star that will give us a reject proposition, okay? So in order to calculate P star, we need to figure out if our alpha was 0.05, then this area here, right here to the right of this P star, will be a reject proposition. Anything to the left will be a fail to reject proposition. So to find P star, we just need to go to the calculator and basically do an inverse norm of 0.95 with this mean and this standard deviation. Okay, so go ahead and do that and calculate your P star. Okay, so our P star was 0.074, and if you have questions on how to find that, but it should be just an inverse norm with this of 0.95 with this mean and this standard deviation here, 0.06, and this right here. Okay, so we found this P star. Now, that is our reject value. Down here represents our 0.075 with this standard deviation. This represents reality. It's unbeknownst to us, but what's happening in the background is really the true probability of something happening. And so in this case, we went out and we got a P hat of 0.075. So this is the true, we're assuming that is the true proportion. And so from up here, when we ran our test statistic, we found since P star is 0.074, we found that 0.075 was actually inside the critical region. Now, if I drew this down right here to this value, I'll change this to red, then this is 0.075, okay? And if this is 0.075, then 0.074 is to the left of that, okay? And 0.074 is our reject value, okay, right here. And that's 0.074. I'll change that to blue. In fact, I'll do that here, 0.074. Now, to calculate the power of the test and the probability of a type 2 error, For a type 2 error on a greater than test, this is going to be whatever the probability is, because if we wanted to know what is the chances of us, it's the borderline of reject in our hypothesized null proportion. So if this is the borderline of reject, then anything to the left of it will represent a failed to reject proposition. But because P is actually assumed to be greater than, P is assumed to be greater than P naught. In other words, 0.075 is assumed to be greater than 0.06, then we should be rejecting. But if we get a P that is less than 0.074, we're going to be in this region here in reality, okay? And the probability of that happening is, find the z-score here, which is, it should be, I think, z equals 0.074 minus 0.075. I think this is actually 0.0738 on the answer sheet, but and it's divided by this standard error here. I'm not going to plug that in right now, and then you end up with a negative 0.128. So the probability that z is less than negative 0.128, you can figure out how to do that. If you don't know, please see me, 0.449. And so that is the probability of a type 2 error. Okay, so the probability of a type 2 error is 0.449. That means the power of the test is everything to the right of that, which is this area here, which would be 1 minus 0.449 or 0.551. And so if you have any questions about this, please let me know. Remember that this value that we're using here is the cutoff for reject or fail to reject based on our null hypothesis. We are then moving that value to see where it fits on the curve of our assumed real parameter. And that gives us the ability to calculate type 2 probability of a type 2 error and the probability of Rn power. So this is power, the green, and the blue, probability of type 2. Okay, see me if you have any questions, and have a nice day.